So we're going to start out today just practicing a little bit of what we did yesterday, mostly with the power rule. Some of it will be trig stuff, just to make sure we're doing okay and understand what we're supposed to be doing with these integrals. So first one, negative x to the negative 2 dx. If we want to find the function that represents the integral of that, we're going to use the power rule in reverse, right? Right. So we'll go up from negative x to the negative 2 to negative x to the negative 1. And then we'll divide that by negative 1 and add a constant. And so that should just become 1 over x plus our constant. Good or no?
Great.
All right, what about the next one? In fact, why don't you guys do the next one, and then we'll see if you got it right. That'll be fun. Do the next one. And what do we get?
3/5 x to the 5th.
3/5 x to the 5th, that's good. And then the next part?
Plus 1 over x squared.
Plus 1 over x squared. That goes up to x to the negative 2, which is 1 over x squared. And we divide by the negative 2 to cancel off the other negative 2. So good. And then what about secant squared?
Plus tan x.
Should just be plus tangent x. Plus a constant. And don't forget your plus a constant. All right, what about the next one? What's this one come out to be? That's a rule straight off of your integral sheet.
Inverse tangent? Inverse sine?
Nah, not inverse sine. You were right the first time.
Inverse tangent.
This is inverse tangent of u plus a constant. Remember, what's the inverse tangent's derivative? It's 1 over x squared plus 1 if it's inverse tangent x, right? Or inverse tangent u is 1 over u squared plus 1. And this is just inverse tangent. So you guys got to memorize all those rules. Make sure you memorize all those rules on that sheet. What about this one? What about 2e to the x? What should you get if you integrate 2e to the x? Well, what's the integral of e to the x?
E to the x.
Should just be e to the x, right? So the integral of 2e to the x ought to just be 2e to the x. The integral of 7e to the x should be 7e to the x. The integral of 8e to the x should be 8e to the x. Yeah? Yeah. All right. What about secant x tangent x?
Wait, isn't e to the power of 2x equal to 2 times ex though?
No, it's
Like no,
derivative of e to the 2x is 2e to the 2x.
Oh.
So derivative of e to the x is e to the x. Integral of e to the x is e to the x. Derivative of 2e to the x is 2e to the x. Integral of 2e to the x is also 2e to the x. Good? Everyone good with that or no?
Yeah.
All right. What about secant x tangent x?
Just secant x.
Should just be secant x. Okay, and then what about the minus root x. That's an x to the 1/2, right? So what does that become? Should become x to the 3/2, and we'll divide by 3/2 or multiply by 2/3. So minus 2/3 x to the 3/2, and plus a constant. Everybody good there or no?
Yeah.
All right. Perfect. Let's do some more. Let's do a definite integral here. So we are looking for the integral from -1 to 3 of x cubed plus 1. And how will we go about doing that? We'll need to find the integral of x cubed plus 1. What's the integral of x cubed plus 1?
X to the 4th over
What?
4.
X to the 4th over 4 plus,
C.
what's the integral of plus 1?
1x.
Yeah, plus x.
Or plus x.
And so now, everything we've done so far with these was an indefinite integral, and we added this plus c to it, right? Well, when we do a definite integral, we don't actually have to add the plus c to it. And the reason for that is, and I'm going to just show you in a second, if I put the plus c there, we can put it there. What do we need to do with this? We need to evaluate this at which two values?
-1 and 3.
Right, the second part of the fundamental theorem of calculus is evaluated at -1 and evaluated at 3 and find the difference. And that's the notation that I'll use. Is I'm going to say, if I'm going to evaluate this expression from -1 to 3, we just write it like this. And that means find 3 to the 4th over 4 plus 3 plus that constant, and then subtract -1 to the 4th over 4. Wow, my handwriting is really bad. -1 to the 4th over 4 minus 1 plus that constant again, right? And so what's going to happen with those two constants?
They're going to cancel.
They're going to cancel each other out. And so when we do a definite integral, those constants don't matter. We don't need to put them in at all. So everybody see that?
Yeah.
So from now on, we're not going to bother to do that with the constants. So now all we got to do is just figure out what 3 to the 4th over 4 plus 3 minus -1 to the 4th over 4 minus 1 is. And let's see, what's 3 to the 4th? That's 81, right? So we got 81 fourths plus 3. And then minus a 1/4. And then minus a -1 ought to be a +1. So we got 84, which is 20, plus the 4 ought to be 24. Good or no?
Good.
All right. Anybody have any questions, any issues, any problems with any of this integral stuff that we've done so far? No? All right, that's good. Let's do another one. What should we do with this one? The integral from -1 to 1 of r plus 1 squared.
Would you factor it out first? Just do it from here.
So as of what we've done so far, there is no way for us to just do this one as is. We're going to have to expand it out first. Yeah, so we're going to do that. So we could rewrite this as an integral from -1 to 1 of r squared plus 2r plus 1 dr. Good or no?
Good.
Okay, cool. So now we'll integrate. What's the integral of r squared?
R cubed over 3.
And the integral of 2r?
to r squared over, yeah, r squared
Just r squared, right? And then what about the integral of 1?
x or r.
R. And so we will evaluate that from -1 to 1, which means we will plug in 1/3 plus 1 plus 1 minus -1/3 plus 1 minus 1. And what is that going to give us here? The plus 1 minus 1 will cancel. This just becomes a third plus 1 plus 1 plus a third, which should be 3/3. Good or no?
Good.
Cool. All right. Are we getting the hang of these integrals or no?
Yeah.
What if I gave you, I'm going to make up a couple more here before we move on. What if I gave you something like this? The integral of root x times x minus 1 dx. We'll just make that an indefinite integral this time. How would you go about evaluating that? Any
The
thoughts?
x is just x to the 1/2 power, and so we can do it that way. The square root of x, I mean.
Yeah, the square root of x is an x to the 1/2, but it's being multiplied by this x minus 1. And so whenever we have the multiplication going on, we can't just integrate each piece of it, because that'd be like sort of breaking the product rule rules from derivatives. So what do you think I need to do with that root x? Just kind of like what we had to do a minute ago with this one. What do you think we should do with it?
Distribute.
Yeah, distribute it out. So x to the 1/2 times x to the first ought to be x to the 3/2, and then minus x to the 1/2. And then from there, we should be able to find what the integral of that is. So what should it become?
Two-fifths x to the 5/3.
2/5 x to the 5/2. So
5/2.
minus
2/3 x to the 3/2.
plus a constant. Everybody good with that? So if you see an expression like that where it's got terms inside of it that are being multiplied together, you're going to need to distribute them through. Everybody good with that? Anybody have any questions on any of the integration that we've been doing at all? So what I'd like you to really quickly do is take a look at the integral assignment that I posted yesterday. Don't worry, we're not done with our lecture for today. But for just a second here, I want you to take a look at that. And I want you to look at problem number 1. And let's see. Looking at A through J on number 1. You all looking at that, A through J on number 1 there on that integral practice sheet?
Yeah.
All right. You should be able, as of this moment, to do everything on that list, A through J. Anybody feel like they have an issue where they wouldn't be able to do one of those that we might need to talk about?
Can you do J?
Sure, J is similar to the one we had done earlier, not today, but yesterday. I'm not going to do J, but I'll do one that's similar to J. So let's say we had something like the integral of 3y cubed minus 5y squared over 2y to the, let's make this 5y to the 12th over 2y to the 4th. That'll be a good one. dy. So that's similar enough that you'll still be able to do J on your own, hopefully. But we can get an idea of what needs to happen here. So what should we do first here? Anybody have an idea?
Bring the 2y to the 4th to the top.
Okay, how would we do that?
By doing a negative y to the negative 4th.
Okay, so we could make it a y to the negative 4th and bring it to the top. That's one option. The 2 will still stay in the denominator though. And if I have a 2 in the denominator, what can I do with that? It's a constant, isn't it? So can't a constant be pulled out of the integral sign? So 1/2 out in front. And then we could write this as y to the negative 4 times 3y cubed minus 5y to the 12th dy. Everybody good with that or no?
Yeah.
Okay. And so then we would take that y to the negative 4th and distribute it through. So 3y cubed times y to the negative 4th should be 3y to the negative 1. And then we should get minus 5y to the 8th. Everybody agree with that?
Yeah.
Okay, now real quickly, I just off to the side here, I want to say, had we taken that 1/2 out over here and just left it as 3y cubed minus 5y to the 12th over y to the 4th dy, that would still become this, right? We would just divide the y cubed by the y to the 4th, and that'd give us y to the negative 1, and the y to the 12th divided by the y to the 4th to get y to the 8th. So either way that we go about it is fine. You can bring that y to the negative 4th up and distribute, or you can just divide the terms one by one by that denominator. Everybody see that both of those would yield the same integral to find in the end?
Yeah.
Yep.
Okay, cool. All right, so now we're working with this. So we've now got 1/2. And what is the integral of y to the negative 1? Can we use the power rule on that? Yes, no, maybe. What would happen if I tried to use the power rule? I'd raise up from y to the negative 1 to y to the
0.
0 and divide by 0, which is going to be a problem, right? So that's not going to work. There must be a different rule on that rule sheet. What is the integral of y to the negative 1? Or how could you rewrite y to the negative 1? Isn't 3y to the negative 1 3 over y? What function, if you took its derivative, would give you something over the variable? Should be right there on your integral rule sheet that's in the Google Drive. What should the integral of y to the negative 1 be?
0.
No.
All right, 1, I meant.
Still no, it's on your integral sheet. You got to look through your integral sheet. Remember, this is 3 over y. So what function, when you take its derivative, gives you something over the variable?
Natural log of u.
Natural log, right? So if I take the derivative of natural log, it gives me 1 over the function, right? Natural log of x's derivative is 1 over x. So the integral of 1 over x ought to be natural log of x. And so this becomes 3 natural log, and it happens to be an absolute value of y. And I'll explain why it's an absolute value in just a second. But what does the second part become? Should become minus 5/9 y to the 9th plus our constant. And there's our answer. So everybody see first off that the integral of 1 over y, or y to the negative 1, should be natural log of y.
Yeah.
Okay. So I said you guys got to go in there and you got to memorize all those integral rules. All right.
What folder is the integral rule under?
It's in the other documents folder in the Google Drive.
Okay, thank you.
It says, I believe it's titled derivative and antiderivative formulas, or derivative and antiderivative rules, or something like that. So it's got all the derivatives, and then on the back side of it's got all the integrals, or the second page of it. Normally I'd photocopy it for you guys, but that's not a thing this year. So everybody good there or no?
Yeah.
Okay. So if I gave you, I'm just going to give you a real simple integral then here. What if I gave you just this integral, the integral of x to the -2 times x plus x cubed dx. What would you do first?
Distribute.
Okay, distribute it out, which would give us an integral of x to the
Negative first.
-1 plus x to the first, right? Dx. And what would that integral be?
Natural log of the absolute value of x.
Natural log of the value of x, and then plus
X squared over 2.
x squared over 2 plus a constant. All right. Everybody good or no?
Yeah.
Okay. Cool. So why does it become an absolute value of x? The reason it becomes an absolute value of x instead of just a natural log of x, right, is normally when we take the derivative of natural log of x, we get 1 over x. There's no absolute value involved. 1 over x, if you think about that, what is the domain of that function?
Everything but 0.
Everything but 0, right? It's -infinity to 0 and 0 to infinity. And so if the antiderivative of this, if it was just natural log of x, what's its domain?
Zero to infinity.
Right, natural log of x is just 0 to infinity. So that only encompasses half of the domain of the original function. And so that's why I put in an absolute value, so that the domain is the same as 1 over x is. Right? And so that way we can put any negative number into there as well. Does that make sense?
Yeah.
So that's why the integral of 1 over x gives an absolute value in there, but you don't need to have an absolute value on it to take the derivative. Cool. All right. Any other ones from A through, what was it, A through J, I think I said, that looked like you might have trouble with them? All right. Then we're going to move in and start talking about something that's going to make it even more complicated, but allow us to integrate tons of other functions like the rest of the ones on that sheet, besides just A through J for number 1. So I'm going to give you 2 functions, f of x, which is x cubed plus 1, and u, which is x squared. And what we're going to try and do is we're going to try and find 3 different antiderivatives, and we're going to put them all in terms of x at the end after we're done doing all of our integration. And we're going to look at how having a different variable, so between x and u, affects it, and how having a different constant of integration here, dx or du, will affect it. And my biggest point here to begin with is that in order to integrate something, this variable has to match up with this variable. And this variable has to match up with this variable. This has to match up with this, which it doesn't. So that's something we'll have to fix as we go through. And so anytime you integrate, this variable has to match with this. Everybody, because we're going to start having multiple variables thrown into stuff soon. So you have to have the same variables throughout. Good.
Yeah.
All right. So integrating f of x dx should be pretty easy. That's the integral of x cubed plus 1 dx. And what does that become?
X to the 4th over 4 plus x.
Yep. X to the 4th over 4 plus x plus our constant, right? And what about f of u du? Well, what's f of u?
X squared. Oh,
No. All right. People always like to do that, right? Put in the x squared, right? Well, no, because what do I need the variable to be? In order to do the integration, the variable is going to have to be a
du.
a u, right? And so what's f of 2? Isn't it 2 cubed plus 1? Of 3. Shouldn't that just be 3 cubed plus 1? What about f of a? Wouldn't that be a cubed plus 1? So what should f of u be? In terms of u, it should just be u cubed plus 1, right? Everybody agree that that's what f of u is in terms of u?
Yeah.
Okay. All right, hold on one second. Okay, sorry about that. So what do we get if we integrate u cubed plus 1 du?
X to the 4th over 4 plus x plus c, or u rather.
U to the 4th over 4 plus u plus c, which if we convert it into terms of x, since u is x squared, what does that give us? It gives us x to the 8th over 4 plus x squared plus c. And so we can see that these two things, if I have f of u du and f of x dx, those are very different, right? The variables and what they're defined as greatly affect the value of the integral. So what about this one down here, f of u dx? So that would be u cubed plus 1 dx, which is a problem. Why is that a problem?
The variables don't match up.
Yeah, the variables don't match up. So how do I make the variables match up? I need to turn this u into terms of x so that I can integrate it. So what is u cubed plus 1 equal to in terms of x?
To the 6th plus 1.
Yeah, x to the 6th plus 1 dx. And now we should be able to integrate that to get x to the 7th over 7 plus x plus a constant. And so we should see that these u's and these x's really do matter. They really are going to mess things up if they're not the same variable. True?
True.
Right, if you do something, if you have two different functions, like if you have a composition of two functions, but you do it with the wrong variables, you're going to get the wrong answer. So we've got to be extra careful about that. So what we're going to do is we're going to use that idea of this composition of functions, u equals something in terms of x, to try to find a way to write out some more difficult integrals into an easier form for us to integrate. So we're going to start off with this one, sine x times e to the cosine x. And effectively what we're going to be doing here is we're going to be doing the chain rule in reverse. So we're going to sort of undo the composition of functions. So we're going to start with this undone version of the composition and rewrite it as a composition of the functions. So any thoughts on what we might want to substitute out here as a u value? But even before we think about that, do you just see a way to integrate this?
What do you mean by narrate this?
What?
What do you mean by that?
To integrate it. Did you just see a way to integrate it?
I heard it wrong, my bad.
Yeah, I thought you said narrate. That's why I was confused, because I didn't think I was
That's
narrating.
why I was confused. That's what I heard.
Yeah. I mean, I'm sort of narrating my own lecture here, I guess, but no, that's not what I meant. Anybody just see a way? I mean, is this just one of the integrals off the rule sheet?
Wouldn't e to the cosine x just stay the same?
No, because it's e to a function. If it was, remember when we take the derivative of e to a function, you have to use the chain rule. So if it's just e to the x, yeah, then it would become e to the x. But this is e to a function, plus it's being multiplied by something else, which causes even more of an issue. Because remember, the terms have to be separated by a plus or a minus for us to just integrate them one by one. So you shouldn't be able to see just a straightforward way to integrate this. What we're going to have to do is we're going to have to make a substitution. So we're going to have to let u equal something within here. And we're going to try and turn everything into terms of u eventually. So generally, when we're doing an integral that requires us to do a substitution for u, and this is called a u substitution integral, we want to look at the most complicated piece of the function. So what is the more complicated piece of this? Is it the sine x or is it the e to the cosine x?
E to the cosine.
Right, e to the cosine is more complicated than sine, right? And so what we want to try to do is try to substitute out, generally, the part of the complicated piece that makes it complicated, right? So if I were to substitute out the cosine x, I would just have an integral of sine x e to the u dx. And e to the u is a lot simpler than e to the cosine x, isn't it?
Yeah.
Yeah. So now we begin to have an issue here, similar to what we were originally looking at in the last slide, right? We have x's and u's, but we have a dx. And we intentionally got rid of some of the x's and turned it into u. So what we want to try to do is turn everything else into terms of u also, including this dx. And so then the question becomes, how do we turn that dx into a du? Any thoughts?
Could you rearrange the u substitution equation so that you have?
Yeah, we are. We're not quite going to rearrange it, but we're going to think about how could I get a du or a dx out of this? What's something we know how to do with an equation to get a du or a dx?
Take its derivative.
Take its derivative, exactly. So the derivative of u is du, and the derivative of cosine x is
Negative sine x.
negative sine x, and we're going to say dx, because we're doing each of these irrespective of what the variables are. We're just taking the derivatives of them. And so each one has to get a du or a dx attached to it based on what variable we're taking the derivative of, just like when we were doing differentials way back when. So now, if we wanted to have a du in here instead of a dx, we'd have to get rid of a negative sine x dx from it. And then we could replace a negative sine x dx with a du, because du equals negative sine x dx. Does that make sense to everybody?
Yes.
Okay. So do I have a negative sine x dx?
Almost.
Almost, right? I have a sine x and I have a dx. Well, why don't I just put a negative in there? Can I just put a negative in there? Can I just multiply this by -1 without changing it?
No.
No, only if I multiply it by -1 again, right? Couldn't I multiply it by -1 twice?
Yeah.
Yeah. And then do I have a negative sine x dx in there? Sure looks like it, right? I have a negative sine x inside the integral and a dx inside the integral. And so all of that can be replaced with du. And so we've turned this into an integral that is all in terms of u, e to the u du. Everybody see how we did that? We found something to substitute out, and then we took the derivative of that substitution to try to build in a du so that we could integrate in terms of u. And what does this give us if we integrate? What is the integral of e to the u? Should just be e to the u plus our constant, right? And what does that give us? It gives us negative e to the cosine x plus a constant. Does that make sense to everyone or no?
Couldn't you have done the kind of the chain rule? Because e to the cosine x, the derivative of that would be negative e to the, or sine times e to the cosine x.
Yes, I mean, that's effectively what we are doing. We are doing the chain rule. We're just doing it in reverse by building in that substitution. So that's exactly what this is. When you do this u substitution, you're doing the chain rule in reverse. And you might have seen off the bat that, okay, yeah, I recognize that the derivative of e to the cosine would be negative sine e to the cosine. And so you could have maybe, through that thought process said it needed to just be negative e to the cosine. But I think in general, it's going to be a lot easier if we get used to building in that substitution.
Okay.
And so with the
and-
negative,
Sorry,
did
go
we
ahead.
multiply the negative by both terms in the integral or just the sign?
It's being multiple. I mean, it's all multiplication in there, so everything's being, doesn't matter what order you multiply them in. It's a -1 times a sine times an e to the u.
Right.
So it doesn't really matter what order you say you're doing it in. Hold on 1 second. All right, sorry about that. All right, everybody good with that or no? Is everybody okay with that problem or no?
Yes, thank
Yeah.
you.
Yep. All right, let's try and do another one. Let's look at the integral of x squared times the square root of 5 plus 2x cubed. Any thoughts on what we might do with this one?
Set u equal to 5 plus 2x cubed.
Yep, that's exactly what we're going to do. So we're taking the more complicated piece of it and substituting out the part of it that makes it more complicated. So we're going to let u equal 5 plus 2x cubed. And what will du be?
Six x squared.
X squared dx. And do I have a 6x squared in there?
No.
Nope, but I could build one in by multiplying by 6, right? 6x squared root u dx. And if I multiply by a 6 on the inside, what do I need to do also? I also need to multiply by
1/6.
1/6. And I'll do that on the outside of my integral. Everybody good with that? And we should see the 6x squared dx right there should become du. And what do we get? 1/6 of what? What's the integral of root u, or u to the 1/2?
2/3 u to the 3/2.
2/3 u to the 3/2 and plus a constant. And this plus a constant could be inside the integral, or sorry, could be inside the being multiplied by the 1/6 or not. A sixth of a constant is still a constant. So don't worry about where that sits right now. And so this becomes, if you multiply that out, 1/9 of u to the 3/2. So 1/9 of 5 plus 2x cubed to the 3/2 plus a constant. Good or no?
Good.
All right, let's do another one. Before we do this one. Let's integrate just cotangent x dx. First thing you should do is look at your rule sheet. Is there a rule for this one? Yeah, looking at your rule sheet, is there a rule for cotangent x?
I don't think so.
Yeah, there's not. So what we need to do then is rewrite cotangent x in some other way. How could we rewrite it?
Cosine over sine.
Cosine over sine. And then what will we do?
Use the rules for the integral of cosine, the integral of sine.
I wish we could, but since they're being divided together, we can't do that.
Oh,
Just like if they're being multiplied, multiplication and division are the same thing, right? So just because of that division, we can't do it. So we're going to have to do a substitution here.
make u be sine.
Sure, let's let u be sine. And generally, if you have something in the denominator, that's what you're going to want your u to be. What does du become?
Cosine x dx.
Cosine x dx. And now we've already got the cosine x dx up there. We just end up with an integral of 1 over u du. And what's the integral of 1 over u du? This one is a rule. In fact, we've also done this one today.
Natural log of u.
Yeah, this is natural log of the absolute value of u plus a constant, or natural log absolute value sine x plus a constant. This is an integral that it might be helpful for you to memorize. It is not on that sheet. You don't have to memorize it. You can always just go through and do this u substitution, but if you happen to memorize it, that might help you out some. You think we could do a similar thing with tangent, with an integral of tangent x? What would we do?
Replace it with sine over cosine.
Okay. And what will our u be?
Cosine x.
Cosine x, and so du will be negative sine x dx, which means that we'll have to put a negative sign inside, which means we'll also have to put a negative sign outside. And we have now got the opposite of the integral of du over u, or 1 over u times du. And what does that become? Natural log absolute value of u plus your constant with the negative out in front. And we end up with negative natural log absolute value of cosine x plus a constant. Another good one to just sort of know. It's not on the sheet, but if you know it, it's helpful and you don't have to do the u substitution every time. Sometimes you might also see this written as natural log absolute value secant x. plus a constant, right? Cosine to the -1, right? Which is, the cosine of x to the power of -1 would be 1 over cosine, which would be secant x. So, same thing. Good or no?
But it's not negative.
For the natural log of secant, no. For the cosine part, yes. Right, because if you think about it, remember this -1 that's out in front of it can be applied as an exponent of something inside the logarithm. So it's the natural log of cosine x to the power of -1, not the inverse cosine, but to the power of -1, which then drops that down. Natural log 1 over cosine, or natural log secant.
Okay, got it.
So helpful to know those, but if not, it's helpful to know that those are done using a U substitution. So with that knowledge, I'd like you guys to take 2 minutes and see if you can find the integral of cotangent of 7x. So give this a try on your own. Sound good?
Perfect.
All right, ready, go. All right, so what did we do for our U substitution?
Made U equal to 7x.
All right, if we let U equal 7x, then what is du?
7 dx.
Should be 7 dx, good. And do we have a 7 dx inside of here?
No, but we could make one.
Nope, we can put a 7 in there, right? 7 cotangent U dx, that gives us the 7 dx, but then we got to put a 1/7 somewhere in there also. And so this will give us 1/7, the integral of the 7 dx will become our du, cotangent U du, and we now know the integral of cotangent of U, right? This should become 1/7 natural log absolute value of U. Or sorry, not of U, of sine of U. Plus our constant. And then all we have to do is go back in and replace the U with 7x. And so we get 1/7 natural log absolute value sine 7x plus a constant. Good or no?
Yes, but does the du always come like afterwards, or the dx? Or can you write like du cotangent U, or is that wrong?
If you wrote that, that's fine. Generally, the du just signifies that you're done with everything that was inside the integral sign, because I might have some other stuff over here. So normally put the du or the dx at the end, yeah.
Okay, thank you.
I mean, it's all being multiplied together, so it doesn't really matter what order it's in, but yeah. All right. I'd say maybe we stop there. I think we'll stop there. We'll finish these up on Monday. You should now have enough information to do all of number 1 and the first part of number 2, where there's some definite integrals also for number 2. And the second part, because we haven't done any definite integrals with U substitutions yet, we'll take care of that on Monday. And that assignment will be due by the end of the day on Monday.